to program this, not so easy to program that. Okay. So any questions? One example is enough, right? Or what is the code here? Is it still doing it? I don't know. The tapes usually are 2 hours long, right? But how do you change from LP, SP, this? You know what I'm talking about?
Good shot.
You can extend them so they give you any output you want. Okay. This is called a Moore machine, a Moore FSA. The difference is, it's like the one we just did, but every node is associated with an output that you produce when you visit that node. So inside every node, you want to print a 3, if you ever get there, put a 3 in there. How it works is, if you see an A in the input and you're in this state, you go to that state and you see out a 3, you print a 3. So I can produce outputs using this notation. It's still a finite state automaton. I have if statements and states. The only difference is, in his program, when he said if current state is 1 and input is A, then current state is 2, I have the option to stick then current state is 2 and see out X. It's still an easy program. So I can print. Now, here is an FSA, an example of a non-deterministic FSA. What does it do? It will do the binary addition. It's a binary adder. Okay. How does it work? Let's say you have two binary numbers you want to add. Okay. Of course, the answer should be 1 plus 1, 2. 1 plus carry 1. 1 plus 1, 2. 1 plus 1, 2. 1 plus 1 plus 1, 3, and carry 1. That's the answer. Okay. This binary adder, this is a program to do binary addition. Okay. How does it do it? Well, to feed input in the FSA, you have to give me a string, a sequence of characters. So what I'll do is I'll take the things I want to add, I'll take one by one. And I want to add right to left. So the input to this guy will be on the tape, it will be 1, 1. Okay, the digits I want to add. 1, 1, 0, 1, 1, 0, 1, 1. That's the input stream that I'm trying to read. Now, as he's reading, he will be changing states and he will be producing output. So let's see if he does it right. Okay. I'm in the initial state. I read a 1. Now, this is non-deterministic. You cannot move with one symbol. You get to read the next one too. Which actually, I could convert this to deterministic if I wanted, but it would be a really big, ugly one. Too many states to show you. But it would be very easy to program. Right? So in this case, you have to read 2 symbols, right? Every move is 2 symbols. Comma means if you're here and you see 0, 1, or, comma means or. All right, what do I see? 1, 1. Well, go here. What's the output? 0. You visit and you produce the cout, the output. So if this is the input, the output will be 0. Now I'm here. What's the next input? 0, 1. stay here, output 0. 1, 0. Stay here, output 0. And 1, 1. Go there, output is 1. So you got the correct output in reverse order. Because I'm adding this way, right? This plus this, I'm getting the output this way. Okay? Now the carry, you can know the carry by looking where you are at. The carry will be 1, because I'm here. Over here the carry will be 0. So this is a binary adder. Okay. 2 numbers in, a number out. This is not a Boolean function. Now, how did you build that? Well, basically, when you start, you have 4 cases. You're either, right, adding 0, 0, or 0, 1, 1, 0, or 1, 1. So I need 4 arcs coming out of this guy. Did I forget? 1, 2. Yeah, I have 4. 1, 2, 3, 4. So if you start, if you see a 0, 0, what should the output be? 0. So you stay here, you produce a 0. What is the carry? 0. So semantically, what this state means, remember when we were doing the FSAs, we said this means, oh, you have seen your first A. This means you have seen 2 A's in a row. Right? What does this state mean semantically? It means there is no carry. Right? And the output is 0. No carry and the output is 0. If you see 0, 1, the output is 1, so you cannot stay here. Right? You have to change the output. So you put a new state here, the output is 1. How about carry? There is no carry. So this means no carry, the output is 1. Those two are no carries. No carry, the output is 1. What is this? Yes, there is a carry, but the output is 0. And this is yes, there is a carry, but the output is 1 because there was 1 coming from here. So you get a 3. Those are the 4 states. Either yes or no carry, output 0 or 1. 4 possible states. So when you start, when you see 0, 0, the output is 0, no carry. You go to this state. 0, 1. No carry, the output is 1. You go to this state. No carry, 1. 1, 0, same thing. 1, 1. There is a carry, the output is 0. Go to that state. Carry 0. And continue, like from here. What if you see a 0, 0? Okay, there was a carry. You're in the carry state. And you see a 0, 0. The output should be 1, no carry. Where is 1, no carry? That guy. So you go there. With 0, 0, you go there. You're here, you see a 1, 0. You're in a carry state. This means when you came there, you carried the 1. Do you follow? If I'm in this state, I'm saying, what is this state? You have a carry, and you just gave output 0, but you do have a carry. And the next input is 1, 0. Because of the carry, the output should be 0. And you should have a carry. So you want to go to the state, you have a carry with output 0, which is this one. So you stay. 0, 1, you stay. 1, 1. The output should be 1. And you do have a carry, because 1 plus 1 plus 1 is a 3. So that's the carry with 1. You go there. So that's how I connected those. Thinking that way. You have 4 possible states, After you process two symbols, the output is either 0 or 1, and the carry is either yes or no. That's 4 states. Right? And given any state, how did I go to the destination? Thinking, if the input is this, connect this way. That's the binary adder. Two states. If you land in here, output is 0. Here, output is 1. What does that do? Well, let's give some input. Let's say the input to this machine is A, B, D. What's the output? This says if you're here, you see A or B. Doesn't matter what you see. You go there. So A, 1. B, 0. B, 1. Okay. So what will be, if I give you a string, what if I had another B or an A? 0. The output is 1, 0, 1, 0, 1, 0, like that. Okay. If you look at the last digit, when will the last digit be 1 and when it will be 0? No, the empty string will not produce any output because with the empty string you're here, you cannot go anywhere. The rule is you read something, you visit the state, and then you produce the specified output. The empty string doesn't do anything for you. But let me ask you this. This has even length, right? What will the last digit of the output be, 1 or 0? 0. What if this guy has odd length? What's the last digit?
1.
1. So the last digit is either 1 or 0, depending on the evenness, or if this is even or odd. So this is like a parity checker. It checks if the given string is even or odd. Okay. Just look at the output, the last bit you got, and you can tell if it's even or odd. That's what it is. Of course, in this case, because the output is either even or odd, you could do it with a simple FSA, which is Boolean. You want it to recognize odd, make this final, and if it's odd, it will say yes, it's odd. Otherwise, it will say even. So if the thing you want to calculate is only Boolean, two possible values, you don't need to use extended FSAs. You can use the original, the Boolean functions. You had a question. Am I going too fast or it's okay? I mean, don't hesitate to say, hey, what are you doing here? Is the pace okay? What do you think? Not too fast. Okay. All right. Now let's do one more algorithm. Then you will plead for mercy. No, no. If they give you a regular expression, like let's say A star, B star. Well, this is a language. This defines a set of strings. A's followed by B's, 0 or more of them. If they ask you, can you build an FSA, can you write a program to recognize the strings that belong in this language? One way to do it is ad hoc, like you did before. Let's see, should I go or should I stay? Let's go with an A. With a B. But actually there is an algorithm to do this. There is an algorithm that will produce the FSA. Okay. Here is the algorithm. It's very simple actually. It's based on a number of observations. Observation number one. If they give you a regular expression that happens to be an individual symbol, like A, can I build a non-FSA for it? An FSA for it? Sure, here it is. What's the language recognized by him? Is A good? Accepted? Yeah, A, accepted. Anything other than A is not accepted. A, B. You use your A, what do you do with your B? You're stuck, you cannot read it. No good. If anything else follows A because you have no arcs, is not accepted. If you have B's before the A, B, oh, you cannot go, not accepted. BA, you cannot even get to the A, you cannot use the B. So to recognize a single symbol, that's the automaton. Okay, observation number two. Suppose C built an automaton to do language L1. It's already built for you. And he built an automaton to recognize some other language called L2. If you click on the command, I am some command from the book. And at the end, I'm going to add the homework for JFlap. I just have one now. You have maybe one or two more. That's the simulation package. Everybody knows how to download it. And then I have copies of the notes, so you can go and look at the notes. All right, so there are two sets of nodes, and there are links to both of them. Yeah. The homework is at the end, June 2nd. We know what the regular expression is. We know what the not deterministic automaton is, the deterministic automaton. Actually, all those three are equivalent. There are different ways of representing the same algorithm. There is an algorithm you can use if they give you an automaton which which will be this and this because they're equivalent, right? To convert it to a regular expression. So this would be algorithm 3 we're going to do. Then there is a type of grammar. A grammar is a set of rules, right, that defines the syntax of a language. There is a type of grammar called the right linear grammar, and we'll do an algorithm to show that this is also equivalent to all those three. There is an algorithm to take a right linear grammar and build an automaton out of it. Or take an automaton and build a grammar for it. Right? So we'll do those three algorithms. Okay, first, if they give you an automaton, well, if it's not deterministic, you can always compare it to the deterministic, right? So let's say I give you this one. This is a deterministic automaton, right? The question is, can you figure out which language it recognizes? Okay. Well, if you use your human intuition, trial and error, whatever, ad hoc method, sometimes you can answer this question, but it will become increasingly difficult as I have more states. This one would be easy, right? What's the language here? Which strings are accepted by this guy?
Starts with A. Starts with A and only one.
Only one A, yeah. So it has an A followed by any number of b's, 0 or more b's. A followed by 0 or more b's. Now, one way to describe the language will be as he did in natural language. Because you have an A followed by 0 or more b's, or followed by any number of b's. Another way to describe it would be like he did, AB star, using a regular expression. Right? Okay. Natural language is always dangerous with it. You know, if you're not careful how you state it, you might misstate the language. So that's what this algorithm does. Instead of being wide open, can we do it or we cannot do it? You know, what if I start putting here and you know, one more state? If I have 100 states, you will be lost. Okay. So how does this algorithm work? From an FSA, can we get the regular expression, not the natural language, but the regular expression? Okay, what's the algorithm that will convert an FSA to a regular expression? Let's define recursive R, stands for recursive, it's a recursive formula. Rijk plus 1 to be all the strings in sigma star that will take you in the automaton from node I to node J without going through any node labeled K plus 1 or higher. This assumes you have labeled the nodes. Okay, so you have the automaton, you label the nodes from 1 to n. 1 is the starting state. Rijk plus 1 is all the strings that will drive you from I to J without going through any state K plus 1 or higher. What does it mean going through? Okay, the string A, B, A, starting at 1. A, B, A. You just went through state 2. Going through a state means you visit it and then you exit it. So you have at least one symbol to get you there and one symbol to get you out of there. The string AB. A, B. Did you go through 2? Yes. You entered it with A, you exit with B, regardless where you went. You ended up coming back to it, but you went through it. Right? The string A, you did not go through. With one symbol, you cannot go through any state. All right, now this is a definition. Now there is a recursive formula we can use to calculate this. What is this equal to? Okay, let's do a diagram. Here is state I. Here is state J. Right, all the strings that when you start at state I and you follow A, B, C, you follow the string, you will not go through K plus 1. Well, suppose state K is over here. That's the highest state you can go through. Okay, that's the highest label you can go through. So these strings that we get you from here to here, and the highest they can go through is K, will be all the strings